Hey there, brilliant learners. Let's start with a simple question. If two friends climb the same staircase, but one reaches the top faster, who do you think is more powerful? Yup, the one who finishes first. That's what we call the rate of doing work, how fast work is done. In physics, not everyone who works does it at the same speed. You and your friend might both lift the same bucket of water, but if you do it in less time, you've done the same work at a higher rate. We call this rate of doing work power, and we define it as P equals W divided by T. That means power equals work done divided by time taken. So, power tells us how quickly energy is used or work is completed. The faster you transfer energy, the greater your power. Think of it like this. Two electric bulbs, one 60 watt and 100 watt, both light up your room. But the 100-watt bulb glows brighter because it uses energy faster. That's higher power in action. Alright, now that we know what power means, let's give it some numbers and units. In physics, power is the rate of doing work or transferring energy with respect to time. The C unit of power is called the watt, named after James Watt, the man who made steam engines super efficient back in the 18th century. 1 watt means doing 1 joule of work per second. We can say 1 watt equals 1 joule divided by 1 second. That's written as 1 W equals 1 J per S. Of course, in real life, machines and devices do a lot more work than that. So, we use a bigger unit, the kilowatt, where 1 kilowatt equals 1000 watts. For example, a ceiling fan might use 75 watts, while an electric geyser might use 2 kilowatts. Both convert electrical energy into other forms, but at very different rates. So the next time you read the wattage on your gadgets, you're literally reading their rate of energy use, their power rating. Now here's something interesting. Power doesn't always stay the same. Imagine running up a hill. At first you sprint fast, but halfway up, your pace slows down. You're still doing work, but your instantaneous power keeps changing. That's why we use the concept of average power. It's defined as total work done divided by total time taken. We say P average equals W total divided by T total. This gives a realistic value of how much energy you've used on average. Think about it like this. An elevator motor might need extra power to start lifting, but once it's running smoothly, it needs less. We don't keep track of every tiny variation, we just measure how much total energy it used in total time. That's its average power. So average power gives us the true picture of performance when power output keeps changing with time. Let's bring this closer to life. Suppose two athletes, A and B, both run up the same set of stairs. Both weigh the same and climb to the same height, meaning both do equal work. But A finishes in 10 seconds while B takes 20. Who's more powerful? Exactly, A. Because it did the same work in half the time. Power doesn't mean doing more work, it means doing it faster. That's why a powerful bike can travel the same distance in less time than a scooter. Both convert fuel energy into motion, but one does it at a higher rate. Machines, engines, and even humans are often compared by their power output. A higher power rating means faster work or energy transfer, and often greater efficiency. So, next time you brag about your new bike or your gym strength, you're actually bragging about your power rating. Alright, time for a real numerical example. Let's put physics to work. Two girls, A and B, both weigh 400 newtons and climb a rope 8 meters high. Girl A takes 20 seconds and girl B takes 50 seconds. We know that P equals mgh divided by T. Let's calculate. For girl A, power equals open bracket 400 multiplied by 8 close bracket divided by 20. That's 160 watts. For girl B, power equals open bracket 400 multiplied by 8 close bracket divided by 50. That's 64 watts. Both did the same work, 3200 joules, but A is clearly more powerful because she did it faster. So, just like that, we can see how time changes power, same energy, different speeds, different results. Let's wrap this up with a powerful thought, literally. Power is all about how fast energy moves or changes form. It tells us how quickly a machine or person can do work. Remember the key equation, P equals W divided by T, or power equals work done divided by time. Its unit is watt, symbol W, and 1 watt equals 1 joule per second. Bigger machines use kilowatts, and car engines are often rated in horsepower, where 1 horsepower equals 746 watts. A higher power doesn't mean more total energy, it means doing the same work in less time. That's why a high-power motor lifts an elevator faster, while a low-power one takes longer to do the same job. So, in essence, power connects work and time, giving us a true sense of how efficiently energy is being used. And that's the beauty of physics. It doesn't just measure effort, it measures how fast effort turns into results. All right, learners, that's all for today. I hope you now have a powerful understanding of how physics measures speed of work and energy use.